Hey everyone, this is Dr. Jacobs. Let's continue our lecture on one sample z-test. I know that we already began finding the critical values in step 5. I want to go ahead and just start here so that we can go over a little bit of what we went over in class with it, and then I'll continue through the rest of the lecture. So again, step 5 is finding your critical values. When we find the critical values, these are the values that we're going to compare our test statistics against. It's symbolized by capital C, capital V, critical value. So if we want to say that we have a critical value of a particular test statistic that we're doing, we'll use CV as subletters to whatever test statistic symbol of what we're using. So for example, the one sample z-test that we're learning in this unit, the symbol for the critical value of a one sample z-test is Z sub CV. So if you wrote a non-directional hypothesis or hypotheses, you'd have two critical values. One's going to be positive, one's going to be negative. They will be the exact same value though. If we write a directional hypothesis, we'll have one critical value. The way that we determine whether it's positive or negative depends on how we wrote our research hypothesis. This can be confusing sometimes because when we make our decision in step 6 with what we're going to do with our data, it's always with relation to our null hypothesis. But when we're talking about our critical values always are going to determine if it's positive or negative based on how we write that research hypothesis. So if we said that one group would be significantly greater than the other group, our critical value will be positive. If we said that one group would be significantly less than the other group, our critical value will be negative. All right, so finding our critical values of Z, we're going to use that area under the curve table that I gave you all during the unit when we did the area under the curve problems where we're examining student placement into statistics course or prereq math courses or advanced stats research design classes. So if you remember in that area under the curve table, there were 3 columns. You'll want to go ahead and get out your chart already if you haven't. I know that we went over some of these things in class on Wednesday, but we will still kind of continue it. So you'll still want to get it out. All right, so when finding our Z critical value table, we're interested in the Z column and the area beyond Z column. Okay, so when we're finding our critical values for the one sample Z test for an alpha level of 0.05, if we convert our alpha level into a percentage, we find that we're okay with the probability of making a type 1 error up to 5%. Once we get to that 5% cutoff, we're not okay with making a type 1 error if we reject our null hypothesis with the sample that we have. So if we wrote our hypotheses directionally, the entire 5% will go on that one side and one tail. Remember, that's actually, if we can write our hypotheses directionally, we want to. And it's for this reason exactly, because if the whole 5% goes on one side, that draws that critical value in closer to the 0, which means we don't need as big of a difference between our sample mean and our population mean in order to find those significant differences, which is our goal. Now, if we wrote our hypotheses non-directionally, then that means that we're conducting a two-tailed test, and we'll need to split that 5% in half, which results in each tail having only 2.5%, which is going to draw those critical values out further away from 0, which means then we need a bigger difference between our sample mean and our population mean in order to say that they are significant differences. So again, that means the proportion of data in each of our tails, if we're going to convert that percentage into a proportion, that we're going to be looking for an area beyond Z of 0.0250 if we're doing, if we wrote our hypotheses non-directionally because we're doing a two-tailed test. All right, so we did this in class, but we're still going to review it just so we have it one more time in our brains. So if we're going to find our critical values for a two-tailed test, we're going to use that area under the curve table. Hopefully you have yours out in front of you. We're going to split that alpha in half. So our alpha for this one was 5% or 0.05 if we're looking at it in percentage form or in proportion form. So again, if our alpha is 0.05, that means for a two-tailed test that there will be 0.0250 in each tail. To find the Z-score associated with an area beyond Z of 0.0250, what do? This is that Dora Explorer moment. This is why in-person classes are so much better. So what do? Make sure you answer before moving on in the lecture. Hit that pause button if you need to. Okay, so you'd look for the area beyond Z of 0.02 0.250, and then find the corresponding z-score to it, and that's going to be your critical value number. So here we'll see that we'd have that critical value on the right side. We'd also have it on the left side of 0. So one will be positive, the one on the right will be positive, the one on the left will be negative. So if we go into the area under the curve table, I kind of replicated the chart into our notes. We find that the z-score associated with the area beyond z of 0.0250 is 1.96. This means our critical values for a two-tailed test with an alpha level of 0.05 will be plus 1.96 and negative 1.96. And so then when we're drawing our normal curve, we'll have our critical values that separate our decision areas, and we would label those on our normal curve when we go to make decisions. And something that's interesting with one sample z-test that doesn't happen with other statistical analyses that we're going to do, these actually will always be our critical values. For if you have an alpha level of 0.05 and you're doing a two-tailed test, it's always going to be plus or minus 1.96, and we don't find that with other analyses like we do for this one. So finding our critical value then for a one-tailed test, this is the new information. Again, we identify whether the critical value is negative or positive from how we write a research hypothesis. So if we wrote our research hypothesis here, we know H sub 1 means our first research hypothesis, X bar means our sample mean. If we have the greater than symbol, then our population mean, which is mu, we know that our critical value is going to be positive. However, if we wrote our research hypothesis where we had the sample mean is significantly less than the population mean, that means that we're going to have a negative critical value. One mistake that students often make when doing these is that they sometimes will try to write hypotheses all these three different ways. Remember, we only going to write one research hypothesis and one null hypothesis for this whole analysis. So if you choose to write them non-directionally, that's fine. You can follow that path. If you're going to write a research hypothesis where you're using the greater than symbol, you're just going to follow that path for this analysis. Or you could write it where you had your sample mean is significantly less than your population mean. Okay, so since we're running a one-tailed test for directional hypotheses, all 5% goes on that one tail. So when we go to our area under the curve table and we try to find the area beyond z of 0.0500, we find that they actually don't have it there. And so people will do different things to do this. Remember, if we're doing this in real life, we're going to be using software and it will just shoot out our p-value for us. So when doing it by hand, we'll just use the critical value of 1.645 because it just splits the difference in between those two. Okay, so what if our alpha level is 0.01? Remember, we can use an alpha level of 0.05 or 0.01. We're going to use this to practice. For this class, we're usually just going to typically use an alpha level of 0.05, but I wanted to get us some more practice using this table. So if it's a one-tailed test, what proportion of our data would fall beyond Z? Think about that real quick. Pause me if you need to. We're doing Dora Explorer again. All right, so 0.01 or 1% of the data falls beyond that z-score. Then we would go and find the z-score associated with the area beyond z of 0.0100. If it's two-tailed test, what proportion of the data would fall beyond z? Again, think about this before moving on. Pause me. So if we split that alpha level in half, we find that it's 0.005. Technically, if we're using what the table has, it would be 0.0050. And so we would look for the z-score that's associated with an area beyond z of 0.0050. And you can do that within your critical value table yourself. After we find our critical values, then we're going to move into step 6 where we make a decision. To make our decision, we're always going to label our normal curve. Okay, so you're going to start drawing your normal curves. Maybe you won't judge my normal curves as harshly anymore if you're having to draw them yourself. So if we have non-directional hypotheses, remember we're going to have our normal curve that's going to have 2 tails on it. If we wrote our directional hypotheses, we'll have our normal curve with 1 tail. So you're going to want to label the critical value or values, your test statistic value, the reject the null hypothesis region or regions, depending if you wrote your hypotheses directionally or non-directionally. And then you're going to also want to write the retain the null hypothesis region on the normal curve. I didn't add this in there, but often I'm going to put the 0 in the middle as well on the normal curve so that I can orient where my positive and negative numbers are. So if we look at this, this is an example of drawing a two-tailed test with the alpha level of 0.05 and labeling the normal curve. We find that we have our two critical values that we learned was plus or minus 1.96. We're going to see that 0 in the middle that helps us orient where our values would fall. We know that in the middle is the retain the null hypothesis region. If our test statistic is not beyond plus or minus 1.96, we know that we're going to retain the null hypothesis, and we're going to say that we don't think there's a big enough difference between our sample mean and our population mean that we can't confidently say that it didn't happen by chance. Then we have the critical values, which is our boundary that we have to get past in order to reject our null hypotheses. So this makes it really easy. So this is what you do. And then when you calculate your test statistic, you just orient it where it falls on that line so you know which decision that you're going to make. So when we write our results for this, we're going to write them both in words and in symbols. When we write our decision in words, either you will write reject the null hypothesis or retain the null hypothesis. Typically, though, when people write results in research studies, they're going to write it out in symbols. But the fun thing about this, I know it's not really fun, but the thing that I like about this is it actually follows the same format. And once we get through this analysis and we move on to our next one, you'll start seeing the pattern. So it actually doesn't matter if you understand how to conduct some of the analyses that they use in journals. If you learn what this format means, you'll still be able to help interpret the results, which makes them a lot less intimidating. Okay, because this is the part of research that usually scares students the most when reading it, but it just follows a template. So if we look at this one, we see that first you're always going to have the symbol for the test statistic that we ran. So for our example that we did in class, and I want you to be able to go through that in class example while we work through this in the lecture. So you'll want to do that, and we can check back in on Monday on it. We have the Z, which represents the one sample Z test. Equals, then we have that test statistic value that we calculated in step 4. So I had a screenshot this from a previous lecture. I used to teach the steps in a different order, but it's step 4, not step 5, which is why your worksheet had it that way too. So you're gonna have Z equals whatever that test statistic value you calculated was, comma, you're going to put your P, which represents P value. Now, if you had significant results where you rejected your null hypothesis, which means your difference between your sample mean and your population mean was big enough that we think it didn't happen due to chance, you're going to put the less than symbol. Then you're going to put your alpha level. So here we find that it's 0.05. We're going to put a comma. And then when we have significant results, we actually have to move on to the next step, step 7, which we'll talk about in a minute, where we're going to learn something called Cohen's d. The symbol for Cohen's d is lowercase italicized d. So you're going to want to put that on your symbol sheet. And then you're going to put equals and then that value that you calculate in step 7. All right. So that's how you'd write your results if you had significant results or we had a big enough difference between our sample mean or population mean that we don't think those differences occurred due to chance or error. If we had non-significant results where our test statistic value did not go beyond our critical value, we follow a similar template. We write the symbol for the test statistic that we ran. So for this is the one sample Z test, that's going to be lowercase italicized Z. It's going to equal whatever test statistic value we calculated in step 4. We're going to put a comma. We're going to put a P to represent our probability value of making a type 1 error if we reject the null hypothesis with the sample that we have. So we'll have P equals, and then we're going to say n dot s dot, which means not significant. Okay, so if we found not significant results, we're actually done here. We don't move on. We stop. We write that as our results. We'd write retain the null hypothesis and move on. If we had the significant results like we had here, we'd write reject the null hypothesis. We'd start writing out symbols, and then we'd calculate our effect size, and then we'd have our results. Okay, so final thoughts on making a decision. If there are statistically significant results, in other words, our p-value is less than our alpha level of 0.05, you're going to conduct follow-up analyses. If there's non-significant results, in other words, we retained our null hypothesis, you're going to stop here. You won't move on. So if you're doing some sort of assignment, so example, the in-class assignment that we're working on right now, if there are not significant results, you would just write out what you have. You'd say retain the null hypothesis. You'd write out the results and you'd stop here. You wouldn't do step 7. You'd say not applicable. If you find significant results in the assignment that we're doing in class, you'll write out your results and you'll move on to step 7. So step 7 is conduct follow-up analyses as needed or relevant follow-up analyses. And for this, just because we find significant results in step 6, it doesn't mean that those results are meaningful. All it says is that our differences are big enough that they didn't happen due to chance. Okay. So effect size then helps us find or determine how much our distributions overlap. So we have a distribution for our sample, right? We know that a distribution is just how frequently each value occurs in our data set. The way that we visualize that most frequently is going to be a histogram. And so we could build a histogram for a sample. We could also build a histogram for our population. And so what effect size tries to show us is how much do those distributions overlap. So for this, for the one sample z-test, we're going to use something called Cohen's d. So we have that lowercase italicized d, which is the symbol for Cohen's d. Please put that on your symbol sheet if you haven't already. And that's going to equal our sample mean minus our population mean divided by the population standard deviation. Okay, so basically this is just seeing how far apart they are. Again, if you do not have statistically significant results, you will not calculate an effect size. Okay. So it used to be common that people would write the results without effect sizes. What's one problem with that? Shout this out loud before you move on. Pause me again. When we find significant results, again, it just tells us that the difference is big enough that it likely didn't occur due to chance or error. Okay. So if our alpha level is 0.05, we say there's a 95% chance that those differences didn't occur because of error. This is slightly wrong, but it's enough for where you all are right now. However, effect size tells us how big those differences are, and that's why it's really meaningful. So now it's required to include Cohen's d in your results if they are significant. That is for everywhere. And if not Cohen's d, either confidence intervals, which I'm not going to have you do, or some other type of effect size, but you have to report effect size now. And so once you calculate that effect size, there's some guidelines to help you understand how big those differences are. So if you get an effect size up at like once it hits 0.20, that means we have a small effect. If it gets to 0.50 or bigger, we consider that a medium effect size. Once it gets to 0.80, we call that a large effect size. Okay. And so these are just different ways to kind of gauge how big those differences are. So if you have any questions, make sure you write them down, bring them to class on Monday. But this will conclude our one sample z-test lecture, and we'll move on to independent samples t-test on Monday. All right. See y'all soon.